All right, I'm going to go ahead and get started. Hello, everyone, and welcome to the UFS webinar. This webinar is hosted by the National Weather Service Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. I'm Alex Alder, and I'm here to help coordinate and deliver the webinar, and feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you would like to present at this webinar, please send an email for your recommendations to ufs.modeling@noaa.gov, and we will take your suggestions into consideration. Due to the high number of attendees, you will be in listen-only mode during the event, and you will not be able to unmute. If you have questions now or during the event, please submit them in the question window available in the GoToWebinar meeting. And here we've got a little demonstration on how to ask questions with the webinar. So if on the left side here, you'll see if you are joining via the web browser, you'll see a little question icon up in the top corner, and you can ask your questions there. If you're joining via desktop, the controls may start minimized, but usually it's up in the upper right corner where you can see there's a little arrow to open up the full window, and you can type your questions into that question box there. And I'll read them aloud, and then Saeed will answer them as we get any. Today's webinar is about the UFS coastal applications, a brief history and current status, and the path forward. And then I'm going to turn it over to Ufuk, and he will introduce Saeed.
Alex,
yeah.
I think maybe we didn't coordinate on that, so I don't think Ufuk is supposed to kind of introduce me. I don't think he's ready for that. He's going to present tag team with me as a part of the presentation. I can do my best on presenting myself. Sorry, I missed that communication with you. But anyway, I'm Saeed Moghimi, working at Office of Coast Survey, part of National Ocean Services. I did my PhD about wave and storm surge coupling almost 20 years ago, maybe even more. I finished in 2005. So I started in this topic in 2001. So I kind of was one of the lucky ones that could stay in the business of coupling in the past more than 20 years. And again, very lucky to work here at NOAA, National Ocean Services Office of Coast Survey, and also collaborating with lots of colleagues on that front. I am leading a storm surge modeling team. We are developing a storm surge modeling products. Our flagship product is STOPS, Sail and Tide Operational Forecast System. And we do research and development, research to operation, and operational support for NCO with support from academia, partners, and others. And today, I have my UFS hat on. So I'm also leading a unified forecast system, coastal, and at National Ocean Services level. And today I'm going to present on that front. So with that, I think we can jump right in, Alex, if that's okay.
Perfect. Yep.
I think you can make it full screen, like F5 or something like that. I'm not sure if it's, oh, maybe not, but there should be a button to do the full screen or whatever it works. That's fine. Okay, let me know when you're ready.
All right, we're ready.
Okay, so today I want to talk about UFS coastal and applications, a brief history, current status, and path forward. And my esteemed colleague, Dr. Ufuk Trunkoglu from NCAR, active developers of ESMF, NOFC, will accompany me and help me to do this presentation. I will call Ufuk in. I think his mic is open, right, Alex? So he can chime in at some point.
Yes.
So
yeah.
Perfect. So as you can see here, I also want to acknowledge my collaborators, partners. A long list here, and again, this list is not necessarily completed. If you or anybody feel like a colleague contributed to this effort but didn't really acknowledge here, please let me know. Before getting started, I also want to thank you, Alex, and also UFS Steering Committee, UFS leadership for giving me this opportunity to talk to you today. Next, please. So we are developing UFS coastal code base and application to build the next generation coastal ocean modeling infrastructure. And the goal is to support NOS modeling vision. As you can see here, we want to support a variety of different applications like safe and efficient navigation, coastal resilience, search and rescue, spill response, ecosystem health, and more. So in order to do that, we are heavily invested in developing UFS coastal and related applications. Next slide. So during a conversation with one of my esteemed colleagues and partners here, he suggested we start with the interesting stuff. So that's kind of, I reorganized my talk to let's just go jump right into UFS coastal applications and components and hopefully get you interested in and can you hook into this conversation towards the end. So we are going to start with our progress with a variety of different applications. I will start with CCOPS, which stands for Southeast Coastal Operational Forecast System, and then we continue with STOPS 3D Alaska, and then STOPS, as I mentioned previously, is Surgeon Type Operational Forecast System that we are developing at the team. And I'm not going to talk about the two others, but then we continue with a conversation about National Ocean Services unified workflow for UFS, and we will talk about a small progress that we had, also our plans there. And then we go to UFS Coastal Code Base and have a kind of deep dive there. And Ufuk gonna help me and gonna present majority of the content there. Next, please. So CCOPS. CCOPS is kind of designed to be a coupled application in which includes ocean component, as you can see on the right hand side, wave component and data model component. And for the wave component, we are going to use WaveWatch 3, ocean component is SCISM, and data model is only handling the information like atmospheric input or some of the other inputs that are going to be passed to mediator, and then have a two-way coupling, kind of a two-way back and forth with the model component. On the left-hand side, you see the map, and right now the standalone model SCISM is validated and is kind of in the process of testing and implementation on our side at National Ocean Services. Next, please. So we have a draft. This is a draft of a potential plan for a development and implementation of CCOPS in relation to UFS Coastal. And as you can see here, we are kind of taking an iterative plan to start implementation and in parallel coupling together. So as a first step, we are planning to only implement SCISM standalone, ocean model standalone, or potentially ocean model standalone, but still within the UFS coastal executable. And then we are going to kind of continue working on coupling to WaveWatch 3. And then at some point beyond 2027, we foresee that the fully coupled application going to be in operation. Next slide, please. So in order for us to make sure the system works properly, and this is really the way that we come up based on our kind of experience and looking at others, that we start with a standalone model, then we go to only atmosphere wave coupled, atmosphere to ocean coupled, and then we test the fully coupled atmosphere ocean wave. And for simplicity, we also started with the two-dimensional model first, and then we are going to extend to 3D. On the right-hand side, you have a little bit of more informative way of communication of the data, which variables is sending, which variables is being received by different model components. And for the test case, we are now heavily working on the smaller size test case in Dock, North Carolina. Thankful to our colleagues from Army, AirDeck, that provided this test case to us. Next, please. So on the left-hand side, the green kind of overlay is the overlay of the mesh, unstructured mesh on top of the map. And then on the more left up, you see the kind of passage of the storm Sandy that we are going to use for our validation. And bottom left, you see the instrumental and observational locations that we are going to use for validation. Right-hand side on top, you see the water surface elevation comparison. The red is the standalone model. The blue is fully coupled model in 2D mode. And the black dots are the observation. And you can see that we have a good agreement, and we show it for 2 different stations on 2 different water depths. And on the bottom, on the right, you see the wave height and wave period stacked on top of each other, again, for these 2 different stations. And again, we are still working. This is a work in progress. This is not the fully polished model. I just want to give you some update and show you, kind of show the progress we have on this front. Next, please. So moving on to STARS 3D Alaska. So we have started this project concentrating on 2 different aspects. One, coupling to wave on one side, coupling to sea ice on another side. And again, as you can see here in component-wise on the right-hand side, on top of what we had on sea cups, we also have sea ice component. So this is make this kind of application way more complicated. On the left-hand side, also the red kind of area show the Bering Sea. We started to concentrate on the Bering Sea side, and we made a good progress on that. We have a pending proposal at NOS Water Team, and if it gets funded, we are planning to extend the domain to Chukchi Sea on north, as well as to Cook Inlet in south. So that's the plan. Next, please. So starting from the sea ice side, so this is a work that we do very closely with Oregon State University and with great support from WIMS, as well as our active participation and partnership from NOAA side, Storm Stage Modeling team. So from a sea ice side, we have started to run the sea ice standalone for Bering Sea. Then we moved bottom left. We moved to run the sea ice still a standalone, but within the UFS coastal infrastructure. So this time, the data goes from data model to mediator and pass to sea ice. And we got identical kind of agreements with the standalone sea ice. And then now, in the past few weeks or maybe months, we moved to try to do a full couple to a schism sea ice. And I just got the note from one of my colleagues that yesterday or the day before, sorry, that we actually pushed this also a good step forward. And now we have tested the fully coupled sea ice schism. However, I still didn't see the validation and verification. So this is also a work in progress. Next, please. Next slide. In parallel to the work that Oregon State University and WIMS doing on the sea ice side, the team, Storm Stage Modeling team, and WIMS also concentrating on coupling to wave. So this is just a snapshot of the summer season run without including ice. On the left-hand side, you see like a visual comparison to tide constituents, and on the right-hand side, you see the comparison of the surface temperature of the model up to the satellite. And this was a image that was kind of have a GIF animated image that's supposed to loop through different days of satellite and model data, so you see the comparison better. Due to the kind of a technical difficulty, just 5 minutes before this meeting, I had to only use one snapshot just to make sure. And actually, right now we are using a PDF version. So anyway, believe me, things are looking much better than what you see here. Next, please. Now, moving on to unified workflow for National Ocean Services operational forecast systems. So this is a project supported by Disaster Supplement, DRSA. We started to kind of modernize STOP's surge and tide operational forecast system. However, we thought, why not we design it in a way that this workflow could basically represent all of the coastal ocean models running in operation at National Ocean Services. So the vision of this model extended to be a unified workflow across all NOS's operational models. The plan is to have it in a way that enhance the efficiency, have the scalability, as well as ease of maintenance. And again, this was a one-year project. We have a pending proposal on NOAA Water Team, and that proposal is actually to extend it to the whole National Ocean Services operational forecast system, including STOPs and OFSs. Next slide, please. So here is one of our early tries. It is for a STOP's 3D Atlantic component as a starter. But again, as I said, we are writing it very general in a way that it could be applicable to all of the coastal ocean model and even for coupled applications down the line. It's a YAML-based, YAML-driven EC flow-based workflow. And here is you are looking at like how we are dividing it to pre-processing, job submission and processing, and post-processing. And we defined a minimum viable product for this, and this minimum viable product is almost towards the end of it. Next, please. So last year, we got a funding for a seed project with Water Institute, and through that seed project with Water Institute of the Gulf, we have started to put together a more even flexible workflow, and these two efforts is kind of combined right now. As a first step for this, we already knew that it's very difficult to get our external partner, academic partner, to WCAS. It's almost impossible for them, and even difficult for them to get to RDHBCS. And for developing this type of application, which eventually should run on WCAS2, we really need to make sure things are working fine. So we started to work on this Docker container, which is mimicking or emulating the WCAS2 environment. We made a very good progress on that, as you can see here. And just last week, my colleague informed me that he could run a good part of the pre-processing of STOPS 3D Atlantic in the Docker container. So it's a very good progress. And I think this specific product for itself could be opening a lot of doors for more collaboration and collaborative work with outside. I know that other colleagues from other parts of NOAA also have these similar issues. So right now we are using Docker container, and we are developing it in RDHBCS cloud, but we are planning to also have a Singularity container for that moving forward. Next, please. So up until now, I just tried to give you some exciting developments. But here, I just want to pause for a moment and go back and have a flashback and kind of review where we started this journey. Then we have a more closer, in-depth examination of our existing infrastructure, where Ufuk gonna help me. And then toward the end, we want to acknowledge the challenges we have, and not always the sky blue and everything rosy. So we have challenges, of course, and then try to chart a path forward. Next slide, please. So going back to 2016, actually, end of 2016, early 2017, I actually joined the team. And at the moment, Coastal Act project was already had a good momentum. The plan was to couple a surge model, wave model, and inland hydrology model to build a waterside component that could simulate a hurricane after its passage up to 90% or maybe even more than 90% accuracy. Why? The reason was that FEMA National Flood Insurance is only insuring water side of the damages. And private companies, insurance companies, are normally insuring the wind damage side. But as you can see in this image, when there is nothing left from a house or building, only a slab or foundation left, it's very difficult to determine what part of the damage come from water, what part of the damage come from the wind, and that was the goal of this project, to help with that. So NOAA was decided by Congress to be the person who helped with this, basically settling down these type of issues. So we started to develop this fully coupled surge wave inland hydrology, and that was an interagency collaboration, and National Weather Service, National Ocean Service, a different part of NOAA, and even interagency collaboration was going on for this project. Next slide, please. So as a part of that project, we kind of started to put together the code locally somewhere, but then we decided to make it more formalized as a GitHub repository with the Git modules. And at the time, also UFS Weather was picking up. So we also looking at the UFS Weather, trying to learn from best practices there and kind of make our development kind of as much as possible according to the books and so on. So as you can see here, we have a very good collaboration with academia and industry. We already have 18 folks from different institutions, from different parts that we are working together. We started with a few model components, but we started to bring in more ocean components to this. I started with ATSIC, SCISM, then FPCOM, and so on. Next, please. From there, we also started to put together a test suite for that. So we had, at the time, 18 different regression tests for different model components. We could run those in different platforms at RDHPCS and also National Science Foundation, and also adapted this to different job scheduling system. And then at that time, next slide, a breakthrough happened. So we got some funding from IIJA BIL Provision 3. And for the first time, after multiple years of development, we had the honor of having a full-fledged, full-flag developer from ESMF, NOFC team, start working with us. So whatever we have done so far was just a bunch of scientists trying to do their best. But from at this point, Ufuk showed up. Great news. And next, please. So we had a very tough conversation at that time. Shall we continue with coastal app, or we fork from UFS weather model and move to UFS weather and deprecate the coastal app after several years of implementation? We had 50, 60 collaborators, partners, model developers, interagency collaborators in one room for 2 or 3 meetings, 2 hour, 3 hours meetings to make this decision as a community. And the decision was that we want to fork from UFS weather model. And we want to, because of so many benefits that UFS weather model bring to us, including mediator and a lot of other components. And here I'm listing the active developers of the, again, UFS, and there might be some more names I missed here. I apologize. Please remind me to add if you're missing here. So there are model components, there are ESMF people, we have EPIC team, and also some of the people from National Ocean Services. Next slide, please. So let me, I want to just quick check on the time. Okay, I think we are good. So from from a starting point, even when we were developing Coastal app, we wanted to have a community-centric project, community-centric development. And when we wanted to go to UFS Coastal, we wanted to make sure it's 100% community-owned and community-centric development. So we have been using lots of different means of communication. In this slide, I want to concentrate on that one. Top right, you see we are heavily utilizing GitHub platform. We're using discussion board. We are using issues. We are using wiki. We are using roadmap and projects to inform and get input from our partner and developers. We are also holding office hours and monthly stakeholder meetings. And we are actively participating on different presentations on different venues like this one and different conferences. On the right-hand side, on the left-hand side, I also show you the list of current stakeholders. There are testers, PhD students, postdocs, future users, our internal colleagues at NOAA, interagency colleagues. So we are having a list of kind of contributors at this point mainly, and also a lot of external partners. Next, please. So when we were deprecating Coastal App, we wanted to find a new house because Coastal App was developed inside Office of Coast Survey GitHub repository. It's a NOAA owned GitHub repository. It's very difficult to get collaborators, partners there, give them right access, this or that. So for this one, we decided to move UFS Coastal to a community-owned GitHub organization. So ocean modeling is not owned by any government. It is an international organization. Now people from Europe, from all around the world are contributing to codes here. And that's opened up for a lot of more collaboration and collaborative efforts here. As you can see here, we have 40 repositories. Here is not only UFS Weather Model Fork and UFS Coastal App, but we have much more projects and teams are working at the same time on different applications. So we forked from UFS Weather Model here, and we also started this whole new UFS Coastal App as a new application. This is like a boilerplate type application. I think Ufuk will talk a little bit more about that. So, and we started this too here. Next, please. And in terms of, again, I'm sorry because I was planning to show this one as an animation, so and interactive, but no, these are two on top of each other. The one underneath is just a list of GitHub issues. So I think, if my memory serves me correctly, we have almost 70 GitHub issues already collapsed, and we have 53 GitHub issue open and under review and under work. So it's a pretty active, already pretty active community. And on the left-hand side, I'll show you how we are utilizing GitHub projects to kind of do the project management. And this is, we are using Kanban, and we are also using like a list of the issues and everything. But here I'm just showing you the roadmap. It's more like a Gantt chart view that we put together this specific roadmap for our leadership because they wanted to check on this and see where we are at. So we kind of also utilize this feature for informing our leadership moving forward. Next. So I also want to report back on a very successful effort that Epic project helped us to basically initialize continuous integration, continuous deployment chain. This effort was started in 2024. Multiple people helped with that. I just 2 or 3 days ago we had a small hiccup with that, but I think as of few weeks now, or maybe even more, we are already using this for nightly build and full regression test every night. So every night UFS Coastal get compiled and run through all of the regression tests to make sure it is satisfied all of those on Hercules right now. And also we can have an on-demand build and test triggered by any GitHub request, pull request. So as soon as the pull request come in, this is gonna get triggered for running regression tests and testing. And all of the artifacts like compiled source code, executables, everything, result of regression tests are going to kind of backed up to the AWS on the fly, and it's open to public to look at and see what we are doing and where we are at. Next, please. So there is a very nice read. We kind of had this one to report the implementation back in November 18, 2024. I really suggest you guys to take a look on this one. It's like a few minutes read, but gives you a good perspective of the CI/CD and how CI/CD enable us to move from research to operation in a much more smooth manner, and making sure the code we have is always ready to be porting on operation, at least potentially. Next. So here we just want to talk a little bit more about and more in-depth information. On the left-hand side, you see the UFS weather model. On the right-hand side, you see all of the new components that we included. And from here, I like to ask Ufuk to take the lead for the presentation. Ufuk, are you okay? Ufuk?
Hi, can you hear me?
Yes, we can.
Okay, next slide, please. As Syed mentioned about that, the UFS Coastal is basically a fork of UFS weather model. So we are closely following the development happened in the UFS weather model and then regularly syncing UFS Coastal with it. So, for example, by this way, we will be ready to push any development from the UFS Coastal side to UFS weather model. So we have a couple of additional components in here. So, for example, we have 4 different ocean models, in addition to MOM6, which is already found in the UFS weather model. So ATCIRC, FECOM, and CISM are unstructured ocean models. ROMS is still using the structured grid. And we have also a parametric atmospheric model to create some kinds of ideal case for the hurricane. And then we can use that information to force the ocean models. And recently, we also developed a new component called coprocessing component. We developed, I will give more detail about that, but that will help us to find the bugs in the regression test or do some coprocessing. Coprocessing means while your model is running, it could also process the data on the fly, and then you can do whatever you want. So you can write it to disk, you can create some kinds of a visualization, etc. In the application level, we have Sphinx-based documentation. We still need to be extended to cover all the regression tests, all details, but we have a bunch of information over there in terms of workflow usage, model compiling, building, different configuration, etc. In the application level, after a long discussion, we decided to go with the UV tools because UV tools is developed by NOAA. And then the main aim is to, because at this point, every application has its own custom workflow. For example, HAVS, global workflow, and S2S, all those things have their own workflow. The main aim is to use the same workflow for all the application. By this way, the maintenance will be much more easier. We start with the UV tools. Once we start, there was no any support for coupled applications because the initial focus of UV tools is to bring UV tools to short-range weather app. So we had lots of discussion with the development team, and then now we could have a version of UV tools that works under UFS Coastal application that supports DATM, supported provided by the CDEPS data components plus CISM working functionally. So the next step is to add the other components, for example, wavewash tree and other ocean models. The next slide, please. Sites show lots of things about the different configurations, but I just want to emphasize in here again. So we are using CDEPS data components, and then we can force all extra ocean components with the data atmosphere, and then we can run them without any issue. We could also have a capability to couple CISM with wavewash tree in 2-way and 2 different configurations. One is using 2D coupling, another one is using 3D vortex coupling, which is still under development and under testing. And recently we start to bring the CIs to the picture to do more coupling through the CMAPs and the UFS cost. Next slide, please. In the new system, in the UFS Coastal, we have a bunch of regression tests to be sure that along with the development, because UFS weather model is evolving too fast, so there are lots of development over there. UFS Coastal is also evolving inside. We are syncing with the UFS weather model. So along with this mess, in this complexity, we want to test at least our own configurations along with the development. So For this reason, we create a bunch of new regression tests under UFS, under regression testing system framework provided by the UFS weather model. And then we are actively running those tests along with the development. So by this way, we will be sure that we are not breaking anything in terms of the UFS coastal. And then we create a new configuration file for it. So we are not changing rt.conf, which has, I think, more than 200 regression tests over there. So we have an isolated system in here. So this will help us to sync with the UFS weather in a much more easy way. Next slide, please. I just want to talk a little bit more about this new co-processing component, which is called GeoGate. For example, you can see a simple coupled application in the left hand side. So this is only atmosphere and ocean coupled with the mediator. It's working fine, but if you want to do something related with the regression testing system or processing the data along the simulation, you need to do something else. This GeoGate component is basically act like a mediator. So in theory, it's something like a mediator, but once you connect to a component, for example, it could be atmosphere and ocean, it will mirror its export fields to its import fields. So after that point, this GeoGate component will access all the data provided by that component. And then you can process that data, something like the processor, but it's running with the simulation. So you can do, for example, I/O. You can do you can also interact with the Python, and also you can interact with the in-situ visualization tool. Next slide, please. So, for example, there is a simple example in here. So at this point, I think if I was using CDEP's data atmosphere coupled with the okay, I have two different data components in here, atmosphere and ocean, coupled with the co-processing component. Just show the capability, but I also tested with the fully coupled configuration under UFS weather model. So it's very flexible and functional at this point. So you can process the data on the fly and then create a fancy visualization like you see in the left-hand side. So this will create a bunch of data for you. For example, when you run the regression test, you are not sure about it's running correctly or not. It could run, but maybe you could see some issue over the ocean, or you could see some issue over the land. You are expecting a answer change, but maybe that answer change is because of some bug in the code. So this component will allow to you to check the configuration visually when you run it. So, and another possible usage is to, for example, we are thinking about processing the data coming from the ocean model on the fly to create a bunch of products like S100 or S104 or something like that. So we are working on it at this point. The next slide, please. In the application level, we have a prototype version of application using UV tools and supporting data atmosphere and season configuration. I just showed some folders in here, but we are expanding that implementation to cover also the other components. The next slide, please. Running the workflow is simple. It's using UV tools. Once you install UV tools, you just need to build your configuration with some top-level build script, and then there is a single YAML configuration file that needs to be customized for your own needs. At this point, the data ATM SISM configuration just requires the SISM grid. So once you provide that grid file, the vertical and horizontal one, the workflow process all the data that you need to force that configuration, including the lateral boundary condition, etc. So by this way, just bring your grid files, update this coastal YAML, and run the workflow. It will create a run directory for you to submit the job, and then you can run it without any issue. I think my part ends in here, so maybe we can go back to Said at this point. Thank you.
Thank you, Ufuk. Great job. Can we go to next slide, please? Sorry, the last two slides. Again, just want to share the project snapshot here with everybody. Left-hand side is more about project definition. We already did a good job of, I think, hopefully a good job on what the project is about. In terms of the progress, right-hand side on bottom. So we are making progress on CI/CD pipeline, as I mentioned. We are still working on skis and waivers to 3D coupling. We have some issues there. We actually spend a good amount of time on tracking down. In particular, we think that there is some calculations that we need to learn from our colleagues for waivers tree side on how it's calculating the Stokes drift in particular. So we are planning to reach out to them, and we think that at this point their support is really essential for success of the project moving forward. And we also defined multiple minimum viable product. If you look at top right, so those minimum viable product is app level workflow. As Ufuk mentioned, we think we are already having the minimum viable product, but we may work a little bit more on that one, and that's going to be for data model and a schism, and then also minimum viable product for CI/CD, and I think we just achieved it a few days ago. But we want to still extend it. At the moment, it's only working on Hercules. We want to make sure we can use other infrastructure for CI/CD. We continue to do the stakeholder engagement, and as Ufuk mentioned, we are going to work more on documentation. And we are just raising a few points here in terms of the potential risks and some dependencies that we face and could potentially bring some risk to the project. Next slide, please. So this is my last slide, more or less. So the outlook. So where we are going. So there are a few challenges that we have, like a high-level challenges that we need leadership to help us. One clarification that we need is to decide or help us to know what is the relationship between UFS weather model and UFS coastal. We fork from that. We are pulling the changes from UFS weather model, but we are not pushing back any changes from our side. So the components we added on UFS coastal is not yet included in UFS weather model. So we need more guidance on what is the future. Do we are going to merge? Do we are not? And we are thinking that UFS governance, which is right now in preparation, the upgrade of the UFS governance or updating that one, hopefully are going to help us to clarify this relationship moving forward. And then with support from that, we are hopefully going to have more clear support and more definite support from EPIC and R2O pipeline. We are very thankful to EPIC program. The leadership and the team went above and beyond to help us and support us, but more like on a windfall kind of situation, not in the queue. So we really want to get into the project officially and get more active support from EPIC. That's going to significantly impact the development as well as the R2 process. So we think that clarification will help us to be more certain about our plans at National Ocean Services for our operation and upgrade moving forward. So with this, next slide, please. I think we can. I will stop here, and again thank you very much to you, Alex, for being patient with us and working with us through all of this kind of technical, and all of you that take the time to listen and tune in today. Thank you very much.
Thank you, Said and Ufuk. We'll open the floor for some questions.
We have also a few folks here in the room with me, but why not we give a chance to Alex, to people online first, and then if not, maybe we can ask people here if they have any question.
Great. I put up on the screen just how to ask questions within GoToWebinar. So as soon as you submit them, I'll read them aloud. We got one note here from George, and it says, "Great talk, thanks."
Thank you very much.
We can go to some questions in the room then.
Yeah, I'm asking my colleagues in the room, is there any question, clarification?
I have a question, Saeed. If we look at the workflows, we always have the mediator being used between like ocean model and wave model, for instance. Is there any plans for, and for example, we have like the mediator, waves, and then ice. Is there any plans for having a connection, for example, between ice and waves instead of, because now we have ocean to the mediator, waves to the mediator, ice to the mediator, but there's no connection between, for example, waves and ice.
Right, very good point. So my understanding, I think Ufuk has to go. Maybe Ufuk already dropped, so he can give you a more maybe later a more kind of detailed answer. But all the parameters that needed from any model component will be exported to mediator. So maybe wave model needs 2 components from sea ice and 2 components from ocean model. So all of them going to be in mediator and then redistribute based on the need. So basically at the initiation of the application, to my understanding, they're kind of advertising what they need and what they are be able to provide. And those are getting matched at the initialization, and then a mediator should be able to distribute. That's one way. The other way is to have a direct communication. So on a coastal app where we are developing, we didn't have mediator. So all of the components were basically doing a direct communication. So we had a communication between them. Instead of sending to mediator, they were directly communicating. So for 2 components, it might be actually better or beneficial. But if you go beyond 2 or 3 components, it's going to be very messy. So mediator is very essential for like multi-component applications. I don't know if I answered your question, Felicia. Yeah, thank you.
To Saeed, I have a question. So we are talking about UFS coastal. So that means so is it kind of developed mainly focus on the ocean and the land interaction, for example, surge or this type of thing, and river flooding,
Right.
rather than emphasize the open ocean part of the.
So your question is, by naming UFS coastal, do we are limiting us to this, or do we have a specific purpose?
Yeah. Because it's called the coastal. Coastal means it's close to the land, right?
Right. So I think, first of all, this UFS coastal or coastal part is a kind of a legacy name. It was already mentioned in very early UFS kind of documentations. But I think, again, my understanding, and I like maybe others, NOS leadership chime in also for that. But I think from NOS point of view, currently the concentration of the modeling at National Ocean Services is more really around the coastal area. So I would see it like more like a, let's say, shoreline to maybe shelf, and then up until like receiving the water from like the near shore or like inland hydrology. So we want to have inland hydrology connection as also connection to the deep ocean. But I don't think we are, at least up until now, we didn't really have a goal of having the deep ocean. And deep ocean and global ocean were historically was supported by National Weather Services. So they are doing data assimilation and global ocean. So the focus for National Ocean Services is more on a coastal region. So I think from that point of view, I think the names is actually meaningful, but that's my understanding. I might not necessarily accurate.
Thank you.
Of course. Any other question in the room? Good. Yeah, Alex, I think you're good in the room.
Perfect. And we have no more questions online, so I think we can go ahead and end it here. Thank you, Saeed, and thank you, Ufuk. I know he's left, but thank you for your time today.
Yeah, thank you very much. Thanks for the opportunity. Have a good day.